Well, good morning, everyone. We are going to finish off our section today. And the section I'm mumbling about is the series 111.2. It's a huge section. And it's after that, I believe the next section will be the integral test. So let's look at telescoping series. That's where we left off last time. Remember a series where you had something, take away something, you wrote them all down and all that good stuff. That's the kind of guy that we are talking about. So let's pick 11 first, or a version of 11. To be a telescoping series, what you should be is two terms subtracted, right? You know, an A take away B. If it doesn't look like it, because sometimes they don't look like telescoping series, that adds a little bit more difficulty to the problem. You have to find a better way to write it, another way to write it, so that it does match a telescoping series. Now, do you notice how this is the log of two things divided? If I ever see a log of two things divided, I tend to think it's going to be a telescoping series. I'm trying to minimize a window. There we go. So first thing I'm going to do is to realize that that is 9 natural log of n, take away 9 natural log of n plus 1. Are you all comfortable with the algebra of how this is the same thing as that? You can keep the 9 here, or you're actually allowed to suck it out of the square root. So I don't mind, both are equally correct, but some people, I guess for simplicity's sake, you can suck the 9 out. Do you see that if I did that, wouldn't I just have a log of n take away a log of n plus 1? And then just remember that whatever the answer is, it's 9 times. I'm just going to keep it that way because there's less work. Now, when you have a telescoping series, what you do next is quite unique. This is the only situation you kind of do this. What you do is you write down the first 2, 3, 4 terms, dot, 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 a general term. And then shouldn't there be a big battle where lots of things get killed off? And then there's a couple of bits left, and that'll tell you what's going on. So let's see what we have here. If you plug in 1, you get 9 log 1, take away 9 log 2. So that's what happened when I plugged n equals 1 in. Add. Now I'll plug n equals 2 in, and I get 9 log 2, take away 9 log 3. And then I'll plug n equals 3 in, and I'll get 9 log 3, take away 9 log 4. And you can imagine this continuing. And then I'm going to kind of stop at a general value, this fella. If you're interested, what technically I'm doing right now is finding the nth partial sum. Now, when you set these guys out, being Scottish and being very violent, I think of this as a war where things kill things. So I'm going to look for things killing things. And I want to see a lot of carnage. I want to have one of those battles where only 2 people are left standing, you know, like 1 from each team kind of thing. So do you notice that negative 9 gets killed off by that positive 9 log 2? Do you notice that negative 9 log 3 gets killed off by that positive 9 log 3? Can we then make the assumption that if I kept on going, this guy here would get killed by something over there? And that would essentially kill off everybody in the middle. Now, what you have to decide is which one of these 2 also gets killed, right? Because one of these is going to get killed by something over here. Which one is it going to be? And tell me why you picked it, because you know you might be picking it because you guessed. Which one gets killed? And where's the clue, if you like? Which one gets killed?
I chose the negative 9 log plus 1. I think that's what you have there.
So you're saying this one here dies?
That's the one I chose.
Okay. The fact it's not right doesn't matter, because I like the fact that you had the guts to choose it. Maybe if you tell me why you choose it, I'll be able to figure out what's going on, because I'm actually going to kill off the other one.
The only reason I chose that one is because the 9 log to the n and the very first number 9 log to the n never canceled each other out. So
oh, you saw it was just you tried to figure out what would be here and what would get cancelled because of that. Right. So let me try and explain to you why that one dies. And it's really just patterns. Do you notice that in the first term, the first one lived and the second one dies? You see that? You see that number there never gets killed off. Basically, the pattern goes like this. If the first one lives and the second one dies, then when you get to the end, the first one dies and the second one lives. You see there's a kind of reverse pattern going on here. Right? First one lives, last one lives. That's essentially it. So when you do that, you're now left with 9 log 1, take away 9 natural log of n plus 1. And to finish this, we then say what would happen to this expression when n goes infinite, because this is basically the partial sum. So what would happen to this term especially when n is infinitely large? What would you get here? Think brute force. What's the log of infinity plus 1? Well, it's the same thing as a log of infinity. What's the log of infinity? The natural log of an infinitely big number. I think you're overthinking it, guys. Say again, Alex.
Infinity.
Yeah. Right, so what you got here is natural log 1, take away natural log infinity. Would you agree the answer is what? I guess negative infinity. We don't really care about the details. All we really need to worry about is that this one diverges. So once you've done the cancelling and you're left with typically 2 terms, make things go infinite and see what you get. And if the answer you get is a number, it converges, and it converges to that number. And then if the answer is some kind of weird infinity or whatever it might be, then the answer diverges. Okay, let's look at another one. It's a version of question 12. Now, this one is good because this one is 2 guys subtracted, exactly what a telescoping series should look like. And let's see what we get. If you plug in 1, you get e to the a over 1, take away e to the a over 2. I know they can be simplified, but I'm not going to bother. Then you plug in 2, and you get this guy. Then you plug in 3. Normally, by the time I get to this, I kind of know what's happening. And then you plug in your general term. That's essentially Sn. Okay. Let the battle commence. Who's getting killed?
The first term.
So when you mean the first term, which one do you mean by that?
E to the 8 over n.
Oh, you're telling them way at the end. You're right. I was expecting that first, but you're correct. Won't this guy get killed off by this guy? And this guy gets killed off by somebody over here. And the first one lives, doesn't the last one live? Right? We're just using patterns. And she nailed it. So what do I have? E to the 8, take away e to the 8 over n plus 1, right? That's the only two terms that would live, right? The first one and the last one in this case. Now we make that fella go infinite. And if the answer is a number, then that series converges to whatever this number would be. And if it's infinite, it diverges. In this question here, would you agree that it's just brute force? I don't need anything too clever. A over infinity is the same thing, whoops, that's an 8, as 0. And e to the 0 is 1. So we can say that that telescoping series converges, and it converges to this number. Are we comfortable with that, fella? Right. So it has a flow to it, right? The telescoping series kind of all look the same, at least once you get to the point where they're both being subtracted, at least they kind of look the same. Now there's another one on my list. I had a little, wrote them down. Oh, here they are. Who shall I look at next? Oh, actually, that is not a telescoping series, but I'll put it down to show you. I know that one diverges, but it is not a telescoping series. It doesn't even look like it, but trust me, it's not a telescoping series anyway. What test would I be able to use to prove that that one diverges?
The divergence test?
Yeah. In this case here, why is that called K? Oh, okay, if it's called K, so is this one. So we're doing the limit as K tends to infinity of the individual terms. And for speed, the L'Hopital's rule, whatever I used would go in there. We get the answer 1. And according to the divergence test, if the limit of the individual terms isn't 0, right, it diverges. So this could be a half or a quarter and it would still diverge. So looks like we're running short of telescoping series to deal with. And here's one, or at least part of one. Now that doesn't even vaguely look like some fraction take away some other fraction, you agree? That's a single fraction. And somewhere in your Calc 2 career, you found how to do a thing called partial fractions. Can you remember partial fractions? You used it in integration to allow you to integrate fractions that look like that. So I get to do my little sentence. Everything that you've done in Calc and before will one day come and bite you in the bum if you haven't remembered how to do it. So here goes. Partial fractions is a technique that allows us to break a single fraction into its 2 component pieces. In this case, these 2 component pieces. Does that ring bells now? Right, 1 nod, that's a scary start. Now, there are a number of techniques, depends who you got, you know, when you did Calc 2. One's called the general algebraic method, and the other method is called the cover-up method. Does anybody remember either of those 2? Anybody feel comfortable enough to choose one of those methods and tell me how you would do it?
Wouldn't you do the cover-up method for this one?
I certainly would. Now, the thing about the cover-up method is that not everybody got me, because I like teaching that one, right? Who did you learn it from?
Oh.
Oh, me? Okay then. It's the reason I like it is it's pure magic. There's no reason in the world why this method called the cover-up method works. Really, I mean, there is a reason, but it doesn't. It's not obvious. But it's so quick that I like it. Otherwise, you have to spend what 20 minutes doing the other method, right? And it's a pain in the butt. Okay, so for those who have not done this, you will probably, and I'm pretty sure you will, go back and look at this video 3 or 4 times before you figure out what the heck I'm doing. So here it goes. To get the number A, you look at the bottom and it says N. You go over here and you cover up the N. That's why it's called the cover up method. This little baby fraction, you put the number 0 in for N. Why 0? Whatever makes this thing 0. Well, N equals 0 makes it 0. If you plug 0 into this fraction, you get 6 over 1, which gives you 6. And that's the cover-up method finished. Now let's look at the second term, the N plus 1 term. You cover up the N plus 1. You then use the value of N that makes N plus 1 0. The number that makes N plus 1 0 is -1. You plug -1 into the fraction that's left and you get -6. There's your guy. This fella is 6 over N. Take away 6 over N plus 1. Called the cover-up method. Christian, you ever seen the cover-up method? Do you like the cover-up method?
It's a lot easier, so I'll take it.
Okay. Would you agree it makes no sense? There's no reason why it should work. There is a reason. You can go and look it up online and find out proofs of it, but it's kind of cool. So unfortunately, that's the way my working, but never mind. If you plug in 1, you get 6 over 1, 6 squared. If you plug in 2, you get 6 over 2, take away 6 cubed. If you plug in this one, you get 6 over 3, take away 6 over 4. And then you got the last guy. You essentially find SN when we do that. I'm getting a lot of deja vu on this question. Are you? Doesn't this kind of look like the last two? Let's see who gets killed. You get killed by him. You get killed by him. You would get killed by a guy that's over here somewhere. First one lives, last one lives. So in this case, you get 6, take away 6 over N plus 1, right? And I'm running short of room here, so I'm going to skip the next line. Won't you make N infinite, and that becomes 6 over infinity? 6 over infinity is 0. 6 take away 0 is 6. So skip the whole load of working, but doesn't it converge to 6? Are we good on that guy? We cool? Right. I'm going to move it. Last chance. Want to see it? Copy it. Or just as I say, maybe watch this video where I did it. See if I can find another one like that. They're pretty hard to come by because there's so many things going on that they have. You know, you only get to see a couple of anything for the most part. Here we go. This is our last one, and we're moving on to another section now. It even tells you that it's a telescoping sum. I can tell you right now, that question should have been the last question you did. it looks pretty much like that one, and it is, except for one major problem, which we're about to see. So I'm going to do the cover up method over in this piece of paper. It's going to be A over N, B over N plus 3. Okay. Let's get this number A. Cover up the N, plug in 0, 27 over 9 gets you 9. Let's get the N plus 3 fella. Right, cover up that, plug in -3, you get -9. So since there's some marks there that look kind of weird. Do you see that to be a telescoping series, doesn't the first number have to be minus in the second number, right? So 3 minus 3, 2 minus 2, 9 of this, take away 9 of that. So back to this fella, 9 of these, take away 9 of these. Doesn't look particularly painful. It is. You get 9 over 1, take away 9 quarters. Then you get 9 over 2, take away 9 fifths. Then you get 9 over 3, take away 9 sixths. Then you get 9 over 4, take away 9 sevenths. And I'm putting one more in. You get 9 over 5, take away 9 over 8. And then you can do the ... And then you can finish with the general last term. And this one is really awkward. Normally, don't you just get one guy left at the beginning, one guy left at the end, and everybody in the middle gets killed off? Did you notice that? Not this time. This is like the ultimate version of ugly. They shouldn't get anywhere near as ugly as this typically, right? So think of this as a special case that you won't get in a test, right? If you get a telescoping series, it's going to be much more like the ones I did before this. That 9 over 1 is going to live. Do you notice that in that 9 quarters, it takes a while, but doesn't it eventually get killed? Now, does that 9 over 2 live, or is there something coming later that's going to kill it? If you look at the digits on the bottom, can you see that there's not any chance that another 9 over 2 is going to happen? Okay, so that one's going to live. What about this 9 over 5? Will that eventually get killed? Yeah, in fact, we can see it. Now, what about one more guy? Does that 9 over 3 make it out alive? If you look at what's coming after it, is there any chance that there's going to be a 9 over 3 over here? No, that one lives. You're going to trust me on one. This one here gets killed off by somebody there. Now that means that there's a 9 over 1 living, there's a 9 over 2 living, and there's a 9 over 3. See, that's a little bit different. Normally, you only get one fraction, number fraction alive, right? Now, since this one lives, won't that one live? Right? So that means I'm going to have that term. Wait a minute, this one lives. Wouldn't that mean that there'd be a term that I haven't written here, where the one on the right-hand side would live? And that guy happens to be that fella. Are you happy about where that came from? That if you did the next bracket, there'd be a 9 over n plus 2. And since the last one, can you trust me that you get that? That's why this one should have been the last question. Too late for me to move it now. In a way, although I needed to put them, Aren't all of these going to disappear to 0 in a second? So the only things that are going to be not zeros is a 9, a 9 halves, and a 3. Take away 9 over infinity, take away 9 over infinity, take away 9 over infinity. So they're all zeros. And that's 12. 12 add 4.5 is 13.5. 13.5 is 27 halves. And we are finished. Are we cool with that last one? As ugly as it is, it does converge. Any questions?
I have a question. So I was doing number 10. Would we be allowed to pull the numerator out and do it that way? Or
So
is
just
that
have a 9 minus these two wee ones on the top? Yes.
Mhm. Okay,
Yes, totally allowed to do that.
thank you.
Right, let's get started on our next guy then. We're going to look at what's called the integral test. So right now, if you look at the series that we've dealt with, we have a guy called the divergence test. We have no particular order. We have a telescoping series. Guess I could put the word test at the end. We have a geometric series. That's a good start, right? So what's this new guy, which is now going to be, I guess, my number 4? What is an integral test and how does it work? So let's give you the theory and then show you how it applies. If we have a series, and I'm going to call this series, I'm going to write it down this way. Typically when I do series, I write it like that. But can you imagine f of n just means like n squared plus 1 over n, right? It's just a usual expression. But I'm writing it more like a function rather than as an an. That's the only difference. So I have this series. So if you take this series, right, S series, right? So you start with that. And you evaluate the integral from 1 to infinity of f of x dx. Can you remember doing integrals like this, indefinite integrals, right? When you did indefinite integrals, wasn't the final answer the area converges to 4 or whatever the number is, or it diverges, right? Now, you evaluate this. And if it's equal to L, where L is a number, then we can assume that the original series converges. But if this integral from 1 to infinity, f of x dx, if it is infinite, or basically, to be more specific, if it diverges, then our series also diverges. So essentially what the integral test says is, if you want to find out whether a series converges or not, turn it into an indefinite integral. If the indefinite integral converges, your series converges. And if your indefinite integral diverges, your series will diverge. This isn't a proof, but it's a kind of pseudo proof. Can you imagine I've got some function called y equals f of x. If I was doing a series 0, 1, 2, 3, 4, 5, wouldn't I be, well, we'll be starting at 1, right? So can you imagine that isn't the series made up of a lot of blocks which closely approximate the area under the curve? In this case, you see that all my blocks are a little bit bigger, right? But they're very close to it. Does it make sense that if the area under this curve starting at 1 to infinity was a finite number, wouldn't all those little blocks probably be finite as well? Right. And if the area under this curve was infinite, wouldn't all the blocks... Well, I am going to kill that because it hurt my ears and I don't like my ears being hurt. Okay, thank goodness for that. So it wasn't me, someone else's computers doing bad things. So that's my pseudo proof, right? That why does the area under a curve tell you if the series that looks similar to it converges or not? It's because essentially they both behave the same way. Now, it would be nice if the only thing I needed to do was to find the indefinite integral, which means I get my Spiele again. Everything that you've done in calculus in the past, or anywhere else for that matter, will come and bite you in the bum if you can't remember it. So let's suppose I am interested in that guy. Keep it simple. Then according to the integral test, don't I need to find out what that integral does? And if this integral is a finite number, that guy converges. And if this integral is infinite or does weird stuff, that guy diverges. So this is going to test you. Can anybody tell me how you set up an indefinite integral from Calc 2?
You define the, at least in this case, the upper bound as a letter such as b, and then you evaluate as a limit as b approaches to infinity.
You're quite right. I'm just picking t because I think that was the letter we used in the textbook, wasn't it? For some reason, they just like t, I guess. Now, this integral and this one are equivalent. The difference is if you put a bracket around it, we're going to do that guy. Now, to remind you how you have to sometimes adjust things, won't this guy have to be called x to the negative 2 before I can integrate it? Actually, I'm teaching Calc 2 right now, so this is fresh in my mind as well. Can you remember the power rule? So when you want to integrate x to the negative 2, you find its antiderivative, and it's add 1 to the power, and then divide by the new power. And so it's going to be the limit, as t tends to infinity, of this guy, evaluated at x equals 1 and x equals t. Of course, style point says that that guy is much easier to work with if you return them so he looks much more like the original. Now I can plug in my x equals t, take away my x equals 1. Now I am left with negative 1 over t plus 1. Would you agree that that guy is brute force? You can just plug t equals infinite. And when you plug in t equals infinite, I guess technically minus 0, but that doesn't really make sense. And so what we can say is that this integral converges. It happens to converge to 1, but converges is all that matters, which means this guy has now been proven to converge. Now, what some people, unfortunately, I can understand why you want to do that, you want to do a little bit more. You want to say, oh yeah, it converges. And since this integral converges to 1, this series converges to 1. Not allowed. All we can say for certain is that the series converges. And you might say, why can't we say it's 1? Look at my picture over here. Aren't those rectangles a little bit bigger than the real area? Won't my answer converge to a number a little bit bigger than 1? It might converge to 2 or 1.7 or something, but there's no chance in the world that it's going to be 1, right? So when you do the integral test, all you know for certain is that it converges or it diverges. You do not know what it converges to. In this case, you don't assume that it converges to 1. That's an important distinction I want to emphasize here. Now, there's another thing I'm going to emphasize that I haven't done yet. The integral test has some constraints. In other words, you can't just use it all the time, because if you could use it all the time, we'd probably get rid of half the tests that we've got. You remember the divergence test is good, but only for what it does. You can't use it for everything. What's the problem, or what are the constraints on the integral test? And the constraints are, the first one is that f of n must be positive. Technically, all positive or all negative, but you're not probably going to see an all negative series. So it must be positive. That's not too difficult a constraint. And this one is the killer. It must be decreasing, at least for n greater than or equal to some number. So the first 2 or 3 terms, it's allowed to go up or down, or whatever it wants to do, right? The first 10 terms, whatever. But after that point, everything else has to decrease. So if this function, give you an example, sine x, doesn't the sine x go up and then it goes down, and then it goes up and then it goes down forever? You couldn't use the integral test on sine x, right? You couldn't use it on x sine x, or anything probably with a sine x in it for the same reason. Because the minute you stick a sine x in something, isn't there a good chance that it's going to increase and then decrease, even if it's only by a little, pretty much forever. So you have to be aware that it must be positive and it must be decreasing. So now that I've finished that first question, which was this one, before I even got to this stage, I should have checked that I can even use the integral test. So in the question that I've got, f of n is 1 over n squared. So let's do check number 1. Would you agree that this is positive? In fact, I'm not need to prove it. Would you agree 1 over n squared is positive? And we're only talking about n equals 1, 2, 3, right? We don't care. We don't even have values like n equals minus 20, right? We don't have them, right? So yeah, it's positive. So good. Now, how do you think I'm going to prove that that guy is decreasing, at least for these kinds of values then? How do you prove functions decrease in the calc world?
Derivatives?
Yeah. So guess what? We're now going to do Calc 1 as well. Have you noticed in this question you needed to do Calc 1, right? Derivatives. Calc 2, integrals. I guess you could say we also had to do limits at infinity as well, you know, just to add all the other fun. So lots of different things going. Now, if I want to differentiate that, don't I have to call it n to the negative 2? And so when I differentiate this guy, differentiation, so I've got my differentiation on, you multiply by the power and you reduce it by 1, which is negative 2 over n cubed. Would you agree that negative 2 over n cubed, where n is only in this list of numbers, would you agree that that is guaranteed to be negative? So I have now proved that it's decreasing. If your derivative is negative, aren't you a decreasing function? So this little bit here, although when you do your homework, this little bit here doesn't even really come into it, probably, right? You're going to have to integrate, aren't you? Because there's no way of telling otherwise. When you come to do a lot of these questions, the answer is simply going to be converging, diverging. Will you not just pick one of them, and if it's wrong, pick the other one and say, okay, I can do this homework in 2 minutes. I'll just go converge, no, okay, diverge, converge, oh, I got lucky, converge, oh, I got lucky again, diverge, no, okay, converge, and zoom through it. Sure, you'll get 100% in this homework. Won't you also get 0 when I do this question in your test? Right, because you don't know what the heck you're doing, you're just getting the homework over with. So this is self-motivation. You are going to have to do a lot of work just so you can pick one of 2 answers. And I know that can be very disincentive, right? Oh God, at the end of all that work, all I have to do is pick diverge. Why did I do that? You know, can I just guess and move on? But you got to be able to do these because you got to have practice at them, right? You got to understand the math, you know, of differentiation and the situations, integrating, limits at infinity, all that cool stuff. Do you like? Are you comfortable with integral test, at least as far as it goes?
So for the last example we just did it converge or diverge?
Oh, because this one here, this one?
Yes.
Yeah, this one converged because when we did the integral test part, the answer was a number, so it converged. When I did the integral part, it ended up being a number. That means it converges. If you do the integration part and the answer is infinity, I would write diverges, right? This bit is actually the bit that should appear before you even do that. It would be nice, but I'm not in charge of this textbook or the questions. If they had a question like, can you use the integral test? And they give you like 3 or 4 questions where the only thing you're being asked to do is, yes, you can use it, or no, you can't. Because that would kind of at least force you to do this. Can you see how you could quite easily just skip this bit and go straight into the integral bit? Because that bit's going to tell me the answer. Well, it will tell you the answer, but only because this, it's cleared these hurdles. And I suspect in the questions, they're only giving you ones where the integral test works, right? Because it's not a fair question. Are we good? Okay. So, what shall I do? Oh, yeah, I got time for our last question. And I'm going to break my own rules, but that's because we have time issues. I would like to know whether that converges or not. Can you trust me that it is positive and it is decreasing, and eventually you could prove it, right? So the integral from 1 to infinity of x squared over x cubed plus 1 dx. That's going to be the limit as t tends to infinity, or whatever the alphabet you choose, of this guy. Okay, what algebraic method am I going to use to integrate x squared over x cubed plus 1. X squared on the top, x cubed plus 1 in the bottom. What technique from integration calc 2 do you use for that kind of question?
Substitution.
We do. What is the u sub that you should use in this question?
N to the third plus 1, or x to the third plus 1.
Right. Are we cool with that? You remember that? Okay. Now, different professors do slightly different flavors of this. I'm just going to do the way I do it. If yours is a little bit different, keep doing it as long as it's right. I'm cool with that. What I typically do next is I differentiate with respect to x. I then do a thing I call the crossover. And then I isolate the dx. So we'll go over here now. It's going to be the limit. Oops, it's going to be the limit as t tends to infinity of, well, I won't put the limits in, but I've got an x squared over u. And instead of the dx, I'm going to have 1 over 3x squared du. Essentially what I'm doing here is replacing the dx by this. And then it's going to be the limit as t tends to infinity of, cancel these out, 1/3 1 over u du. And that's going to be the limit as t tends to infinity of 1/3 the natural log of u, which then becomes the limit as t tends to infinity of 1/3 the natural log of x cubed plus 1. And it's at this point I then bring in the limits of integration. Are we comfortable with that process of the u subs? Now you may have a slightly different flavor, but you will eventually end up at the same destination. So if you do it a slightly different way, that's fine. But if you got me, this is pretty standard. This is how I do it. So what we now do is we find the limit as t tends to infinity, and I'll plug in t, and I get 1/3 the natural log of t cubed plus 1. Take away 1/3 the natural log of, well, 1 cubed is 1, so I'll do it on my head. You got that? Okay, you want to find out what this looks like when t goes infinite. I'm just going to do a brute force, right? Just make it infinite and see what we get. Okay. Infinity cubed is infinity. And adding 1 to it is still infinite. So you get the natural log of infinity, take away this guy. Would you agree that the natural log of infinity is still infinite? And 1/3 of infinity is still infinite. So won't this answer be infinity, take away that number, and infinity? You probably don't need all those lines, but the fact that this integral is infinite, doesn't that mean that the integral diverges? And because this integral diverges, what can we say about this series? It also diverges. So if you kept on adding these weird fractions together, the answer would be infinitely large, right? It just get bigger and bigger forever, right? It diverges.